Welcome back to the deep dive. So today we are standing on the edge of a conceptual cliff.
We really are?
We've spent the last few discussions building this incredibly expensive, very sophisticated pipeline. We tracked a photon of light hitting a sensor,
Right.
watched it get ripped apart into an electric charge, converted into binary, and then, shot through a fiber optic cable across the ocean.
It's a journey we just take for granted, but it's amazing. We've successfully moved the data. The package has arrived.
But that's the thing. If you really look at what we have at the end of that fiber optic line, it's kind of disappointing.
It's just a pile of numbers, zeros and ones.
Exactly. That's the cliff. We have the data, but we don't have meaning. To a computer, that stream of zeros and ones isn't a picture of a cat or a tumor or a stop sign. It's just noise. So the mission today is to figure out how we cross that gap. How do we turn a signal into understanding?
It is the fundamental black box problem. And frankly, it's the problem that recently earned John Hopfield and Jeffrey Hinton the Nobel Prize in physics.
Yeah, and we're not just talking about writing code today. This is the physics of thought.
That's the core of it.
And I think it's important to frame this for everyone listening. This wasn't some overnight discovery. This was a decades-long struggle that almost killed the entire field of AI.
Oh, absolutely. The AI winter.
The AI winter. Before we had the neural networks we use today, everyone bet the house on a completely different horse.
They did. Back in the 60s and 70s, the dominant idea was what we now call GOFAI, good old-fashioned AI.
Which is such a charming name for something that failed so hard.
It was logical, though. You can see why they thought it would work. The assumption was that intelligence is just symbol manipulation.
So if you want a computer to recognize a face, you just describe a face to the computer using logic.
Yeah, that's the symbolic approach. You write a rule. If there is a circle, and inside that circle are two smaller circles for eyes, then it represents a face.
It feels intuitive. That's how we explain things to each other, right? A chair has 4 legs and a seat.
But then reality, it's you.
And reality is messy. I've read about this combinatorial explosion problem. You try to define a chair, and suddenly you're dealing with...
Exactly. You're dealing with beanbags or 3-legged stools or a broken chair lying on its side.
The rule-based system just shatters.
It does. It's the chaos of reality. In the visual world, nothing is ever the same twice. You have shadows, occlusion, rotation, blur.
So if you try to write a rule for every possible lighting condition of a human face...
You'd end up with billions of rules. You can't code the world by hand. The list of instructions becomes infinite.
So the field hit a wall, a huge wall.
And the AI winter set in. Because everyone realized we couldn't program recognition. We had to find a way for the machine to learn it.
And this is where the physics comes in. This is the pivot. The field had to stop looking at intelligence as a logic puzzle.
And start looking at it as a physical system.
Enter John Hopfield.
Yes. And he wasn't a computer scientist trying to write better code. He was a physicist thinking about magnetism and spin systems.
Okay, let's slow down and unpack this, because this is the core of why he got the Nobel. Hopfield looked at how atoms behave in a magnetic material. Is that right?
Specifically, he was looking at spin systems. So imagine a grid of atoms. Each atom has a spin. It's either pointing up or pointing down.
Okay.
In a magnetic material, these atoms interact with their neighbors. They kind of want to align. If your neighbor is pointing up, you want to point up too.
Because that state requires less energy.
Precisely. Nature is lazy. It always wants to find the lowest energy state. The system naturally evolves until it settles into a stable configuration where all the tensions are minimized.
And Hopfield's big idea was, what if neurons are like atoms?
What if they are? So a neuron firing is spin up, and a neuron resting is spin down.
And the connections between them, the weights, are like the magnetic forces between the atoms.
Exactly. If neuron A fires, it encourages neuron B to fire. And Hopfield proved mathematically that a network of these artificial neurons would behave just like a physical magnetic system. It would naturally evolve toward a stable state.
This is the famous energy landscape metaphor. I love this visual. I want you to imagine a topographical map, a landscape with rolling hills and really deep valleys.
In Hopfield's model, the valleys, those lowest points on the map, are memories.
So let's say the network has stored the memory of the letter T. That specific pattern of neurons firing is a valley in the landscape.
Yes. Now, suppose I give the network a corrupted version of that T. Maybe it's missing the top bar or it's all blurry.
Okay, so that noisy input is like placing a ball on the side of one of those hills.
Right. And because of the physics of the connections, the way the neurons push and pull on each other, The state of the network changes. The ball starts to roll.
Gravity takes over.
The system minimizes its energy. The ball rolls down the hill and settles right into the bottom of the valley.
So the network takes the broken T and reconstructs the perfect T.
It completes the pattern. That's associative memory.
It's what we do. If I hum the first 3 notes of a famous song, your brain just fills in the rest. You slide into the valley.
That was the breakthrough. Hopfield showed that computation isn't just logic. It's dynamics.
Yeah.
It's a physical process of settling into equilibrium.
There's a catch with the Hopfield network, isn't there? It was great at remembering things you deliberately stored in it. You could carve a valley for T or A.
Right.
But it couldn't learn those valleys from scratch, could it?
No, and that's a crucial distinction. In a Hopfield network, you'd use something called Hebbian learning. Cells that fire together, wire together. You were basically handcrafting the memories into the weights.
So the network wasn't looking at raw data and discovering patterns on its own.
It wasn't. And that brings us to the godfather of AI, Geoffrey Hinton. If Hopfield built the landscape, Hinton figured out how to make the landscape shape itself.
Hinton took Hopfield's ideas and added statistical mechanics, something called the Boltzmann machine.
Yes, and we're getting into the deep physics here.
Mm-hmm.
Boltzmann is the guy who described the energy of gases. And Hinton realized that if you want a network to learn complex patterns, you need a way to measure error as a form of energy. And he introduced the concept of hidden layers.
This is the shift from just input and output to deep learning.
That's the one. A Hopfield network is usually just one layer of neurons. Hinton said, what if we have layers of neurons between the input and the output that can process features?
But the problem was, how do you train them? If the network gets the answer wrong, how do you know which neuron is to blame?
It's the credit assignment problem.
Yeah, if the CEO makes a bad call, you don't know which middle manager gave him the bad info.
Exactly. And Hinton popularized the solution, backpropagation. And to explain this, let's go back to that landscape. But this time, it's not an energy landscape of memory.
It's an error landscape.
It's an error landscape. The altitude is how wrong the network is. The higher up the mountain you are, the more errors you're making.
And you want to get to sea level, 0 error.
Right. Now imagine the network is full of billions of tiny adjustable knobs. We call them weights and biases. Backpropagation is the math that allows us to calculate, for every single error, exactly which knob to turn and in which direction to reduce that error.
It's gradient descent. I always picture this as being dropped on a mountain range at night in a thick fog. You can't see the bottom,
Right.
but you can feel the ground right under your feet. You can feel which way is down, and you just take one small step.
That is the perfect analogy. The algorithm calculates the slope, the gradient of the error function. It tells the system, if you turn knob 4,300 a tiny bit to the right, the error will go down by 0.0001%.
And you do this for billions of knobs over and over again for millions of images.
And slowly, step by step, the network walks itself down the mountain. It carves its own valleys.
It learns that whiskers and pointy ears usually go together, not because we wrote a rule,
But because that configuration minimizes the error energy when looking at photos of cats, it extracts the structure of reality from the data.
it builds a prototype of a cat in those hidden layers.
Exactly. And this is why the Nobel Committee chose physics. A lot of people were
Oh.
confused by that. They thought, isn't this computer science?
Yeah, that was a huge debate online. But when you look at the DNA of the idea, it's not code.
It's not. The foundational math describes systems of interacting particles finding equilibrium, whether those particles are atoms in a gas or spins in a magnet.
Or neurons on a silicon chip.
The statistical mechanics are identical.
We're treating information processing as a thermodynamic event. The network is cooling down into understanding.
That's it. The Boltzmann machine even uses a concept called temperature. In the early stages of training, you keep the temperature high, you add random noise to the system so it bounces around wildly.
And that prevents it from getting stuck in a small pothole, a local minimum, right? You want it to find the true bottom of the valley, so you shake the box.
You shake the box. And as training goes on, you gradually lower the temperature. The system anneals or freezes into the optimal solution. That is pure physics.
So we've established this incredible pipeline. Light becomes data. Data enters the network. The network uses the physics of energy minimization to carve out these valleys of meaning. The ball rolls to the bottom and the machine says, I recognize this. It's a face.
We have solved the indexical problem. We can trace the path from the object in the real world to the concept in the machine.
But, and this is the pivot that I think is going to define the next decade of our lives, If the machine has these valleys carved so perfectly, can't we do something else with them?
You mean instead of recognizing?
Yeah, instead of dropping a ball in to see where it lands, what if we just pick a valley and start generating?
Reversing the pipeline.
We're running it backwards.
This is the massive shift from discriminative AI, which decides cat or dog, to generative AI.
If the network knows the statistical structure of a face, if it has that prototype we talked about, it essentially has a recipe for creating a face.
It does. You can essentially tell the network, go to the face valley and just sample the probability distribution. You're asking it to dream.
But this breaks the chain, doesn't it? In photography, we always had what philosophers call indexicality. The photo is a physical trace of reality, light bounced off a real person.
That link is now severed. When a generative model creates a face, it isn't remembering a specific person. It is synthesizing a new instance based on the probability of all the features it has learned.
It's sampling from the manifold of faceness.
That sounds like sci-fi, but it's just math. It's picking a point in that high-dimensional landscape that looks like a stable memory, but corresponds to absolutely nothing in the real world.
And that is the cliffhanger. We spent 50 years trying to get computers to see the truth.
And now that they can see it, they can also fake it. Perfectly.
We've moved from the machine that remembers to the machine that imagines.
And the physics is the same. That's the wild part. It is still energy minimization, just run in a different direction.
So next time, we're going to dive specifically into that reverse process. We're going to talk about diffusion models, the tech behind Midjourney and Delay, and how they use this exact same concept of noise to create crystal clear images from static.
We'll see how adding noise systematically destroys information, and then how the machine learns to reverse time to reconstruct it. It's incredible.
It's going to be a mind bender. Until then, think about those valleys in your own mind. When you picture a face, are you remembering or are you generating? Thanks for listening to this deep dive.